Ladies and gentlemen, my name is Martin Horák, and in my presentation I will explain a certain basic property of the electric arc during power system fault. This basic property is misinterpreted in all technical literature available to me and has a significant impact on the fault locator's accuracy. Fault locators are usually used in high-voltage networks, but it's also a very effective tool for locating phase-phase faults on medium-voltage power lines. In Západoslovenská distribučná, the biggest TSO in Slovakia, all medium-voltage feeders are equipped with fault locators. The reactance calculated by the protection during phase-phase fault is recalculated to a specific point on the map in a special GIS application. The long-term analysis that verified more than 200 real phase-phase faults proves that the deviation in fault locating is usually less than 5%, which can be considered a great success. However, in the case of arc faults, the deviation can significantly exceed this limit. In this slide, you can see a radially operated medium voltage line and its representation in the Rx plane. The curve of a typical phase-phase fault is as follows. An external mechanical impulse, for example a tree falling on the line, causes two phase conductors to come close and an almost metallic fault occurs. The protection relay registers impedance in the point A, which is situated on the straight line of the power line impedance characteristic. Conductors then return to their original positions, their distance increases, and an electric arc is formed. All common literature considers the electric arc character as pure resistance. This view is considered a fact, is quoted without further evidence, and most likely originates from synchronous current and voltage drop zero cross. In that theory, impedance measured by the protection relay during the electric arc formation should move in parallel with the R-axis towards point B. Reactance measured by the protection relay should be constant through the entire duration of the fault because the fault remains at the same location. However, this is where the theory and observation differ. From the fault record of the real phase-phase fault, it's obvious that the impedance measured by the protection relay moves towards point C along a straight line with some slope. It's not only the value of the electric arc resistance that is increasing, but proportionally also the value of reactance measured by the protection relay. At the moment when the protection relay trips, it calculates the overall fault reactance, which deviates from the correct one. The protection relay sees the arc fault as farther than it actually is. The key to solving the problem is the VA characteristic of the electric arc during the passage of sine wave AC current. Curve 1 represents the voltage drop in an electric arc during the increase of fault current's instantaneous value in the first quarter of the period until reaching the current's maximum Im in the given half cycle. During the subsequent decrease of the current's instantaneous value in the second quarter of the period, the voltage drop will follow curve 2, which differs from curve 1. Voltage drop will be lower compared to the first quarter of the period. The reason is that during the rapid decrease of the current, essential parameters of the electric arc, as channel cross-section, temperature, and ionization level do not manage to change with sufficient speed, and certain hysteresis of these parameters appears. From this nonlinear VA characteristic with hysteresis properties, we will get a time course of the electric arc's voltage drop, drawn here with a green line. The course of the voltage drop is non-sinusoidal and it contains odd higher harmonics. Fault locators are usually based on the principle of measuring the fundamental frequency current and voltage phasors. The phasor of the voltage drop fundamental harmonic is calculated from the measured instantaneous values using Fourier transformation. The phase shift between the voltage drop and the electric arc phasor and the fault current phasor is calculated using this equation. The cosine coefficient A1 is calculated using this integral. Since the areas under green curves 1 and 3 are larger than areas under curves 2 and 4, this cosine coefficient A1 will be non-zero. This results in a non-zero phase shift between the voltage drop phasor, drawn here with a red line, and the fault current phasor, drawn here with a blue line. During the impedance calculation, apparent inductance of the electric arc appears, leading to incorrect calculation of the electrical fault distance from the feeding substation. This theoretical deduction fully correlates with the observation of this phenomenon during real faults. To verify the theory, we measured an artificially created phase-phase arc fault on a real 22 kV overhead line during full network operation. In this diagram, you can see the network connection during tests. After switching on the circuit breaker, the fault current flowed from busbar W1 through two long lines to the empty busbar W2 and subsequently flowed through a very short unloaded line to the fault point. With this electrical connection, it was achieved that the electrical fault distance was 22 km and the fault current was limited to a reasonable level, while the physical fault distance was only 150 meters. As a result, the oscilloscope installed at the beginning of the faulted line measured electrical quantities almost identical to the quantities on the electric arc. The method of creating the artificial phase-phase arc fault is documented in this figure. Short-circuiting conductors with large cross-section were firmly connected to two phase conductors of the overhead line. Both ends of the short-circuiting conductors were joined with a short coupling of small cross-section. After energizing of the power line, the onset of the fault current almost instantly vaporized the coupling, and a long electric arc was gradually formed. The fault event is documented in the video. This figure shows the measured VA characteristics of the electric arc. Individual characteristics of different colors from red to magenta correspond to individual periods of the fault current in different phases of the electric arc expansion. It's evident that the voltage drop gradually increases due to gradual expansion of the electric arc. In individual half cycles, the voltage drop on the electric arc is higher during the current increase than during its decrease. The mentioned hysteresis manifests itself. Next figure shows the measured current and voltage drop time courses on the electric arc, also corresponding to individual periods of the fault current in different phases of the electric arc expansion. It's evident that in the first and third quarter period, the voltage drop is higher than in the second and fourth quarter period. Standard electrical protection relays based on the principle of measuring the fundamental frequency current and voltage phasors will evaluate a non-zero phase shift between the voltage drop and current of the electric arc. The electric arc is not seen as pure resistance. In the measured impedance, an apparent inductance will appear. The measurement results of the artificially created phase-phase arc fault in the real 22 kV network fully confirm the above stated theory. More informations, for example proposals of the fault locator algorithms improvement, you can find in the full paper. Thank you for your attention.